Today we are starting chapter 2. We are going to be using inductive reasoning. So today we will describe patterns and use inductive reasoning. Today's notes are going to seem pretty drastically different from what we've been doing, which for some people is probably a relief. All right. For our warm-ups, find the length of the segment with endpoints 1, -3, and -2, -7. So I already asked and somebody already answered that we would need to use distance formula to do this. What am I plugging into my x's? Good. So subtracting a -2, it will end up being addition. Square that plus, what about for my y's? Good, -3 minus -7, and that also gets squared. Okay, so yes, you can change these into big old addition signs. Subtracting a negative is the same as adding a positive. 1 plus 2?
3.
Squared. -3 plus 7? Squared. Add them. Square root it. Beautiful. So our distance or length is 5. Two angles are supplementary. What does that mean? They add up to 180. If one is 3 times the other, find the smaller angle. Okay? Well, if we don't know what they are, we could call the smaller one what? X, and the other one would be, well, 3x. They are one that's 3 times the other. So the small one would be x, the bigger one 3x. And we already said supplementary means we add them and set it equal to 180. Okay, it's easy to solve. Combine like terms, what do I get?
4.
Equals 180, so x must equal 45, and that is the smaller of the two angles, so that's all we really need. 45 degrees is the smaller one. Questions on the warm-ups? Okay, move it along. Question: how do we use inductive reasoning in mathematics? Well, if you don't know what inductive reasoning is yet, that might be hard to answer. So I'll tell you, we use inductive reasonings when we make observations. So we notice things about the numbers that we're given. Another way that we could use it is when we check if our answer is reasonable or think about whether our answer is reasonable. Consider reasonableness of answer, however you want to phrase it. Okay, so really anytime that you're noticing a pattern or thinking about how numbers are working together, considering if your answer could potentially be correct, these are all things where we use inductive reasoning. Basically anytime you think about mathematics. Okay, so a definition for us, a conjecture. Conjecture is an unproven statement that is based on observation. Not to be confused with a postulate. Postulates are also unproven, but it's something that is just true. A conjecture, we don't know if it's true or not, initially at least. It's just something that we think might be true based on observation. So that's a big part of it, is the observation part. We use inductive reasoning when we find a pattern in specific cases and then write a conjecture for the general case. we are given the set of figures. We are asked to describe how to sketch the fourth figure in the pattern and then actually sketch it. Now, I believe the ones on your printed notes page, despite the shading not picking up, is a little more accurate than on the board. This last figure should be stretched out a little bit more. On your paper it is, on the board it didn't turn out that way. So we are both asked to describe how to sketch it and to actually sketch it. Now we don't have to be artists, but it should be reasonable. Anyone have a description of how this would look? Or what's happening every time? Deidreana, you want to give it a try? Good. So we've got equally shaded parts increasing by a factor of 2 every time. Or every shaded and unshaded part is getting divided into 2 more parts every time. Something along those lines. So equal parts increasing by a factor of 2. I will not be super picky about how you word it, as long as you're getting the same idea across as clearly. Okay, so if you word it a little bit differently, but it still means exactly the same thing, that's fine with me. So then comes the sketching part. So these rectangles are meant to be approximately the same size overall. Again, on your page it looks more that way than it does for me on the board. So then how many pieces total is this getting split into? 16. That's a lot of pieces for me, so I'm not entirely sure how well this is going to go. All right, so we should have 16 pieces, still alternating which ones are shaded and not shaded. I don't expect you to be artists because I certainly am not one, but it should look close. Okay, if you are an artist, that's great. I enjoy grading that because I like pretty pictures. We ready to move on? Okay, great. All right, this is more my kind of problem. Numbers. Describe the pattern in the numbers and write the next 3 numbers in the pattern. Good thing they didn't ask us for the next 3 diagrams on the last one. That would have been painful. All right, make sure on these problems you're reading all the directions. What 2 things do they want you to do? Okay, describe the pattern and write how many numbers? The next 3. The directions on these types of problems change frequently. Okay, sometimes it'll just say describe, sometimes just give the next 2 numbers. Make sure you're reading the directions clearly. So we've got our numbers 1,000, 500, 250, 125. What's happening every time?
Decreasing by half.
Decreasing by half is a great way to word it. What's another way? Divide by 2 is another way of wording it. Multiply by 1/2. All of these would work. Even if you put a simple division symbol 2. That works for me. Times 1/2 works for me. If you want to write it out in words, decreasing by half, fine. These are all acceptable descriptions of what's going on. Okay? Now for the next numbers. What's the next number? 62.5. After that? 31.25. And after that? Good. Do not round those off or up or down or sideways. Give me the whole number. Questions, concerns about what I expect? Ready to continue. Okay. All right, given the pattern of triangles shown below, make a conjecture about the number of segments in a similar diagram with 5 triangles. Now, sad to say, but on tests and quizzes with problems like this, I would just have students show me the next picture or show me a picture with 5 diagrams. Is that what they want? No. They didn't say sketch or draw. Now, if you sketch or draw to help yourself out, fine. But that is not what the question is asking. They are asking for us to make a conjecture about the number of segments involved. So it might help if we form ourselves a little pattern about what's going on. So, how many triangles do we see first? 1 triangle, and how many segments? 3 segments. On the next one, how many triangles? 2 triangles, how many segments? Good, careful. 5 segments. They're not asking how many segments do you need to make 2 triangles. How many segments are actually here? 1, 2, 3, 4, 5. Next diagram, how many triangles? 3. And how many segments? 7 segments. Now they're asking us about how many triangles? 5. Okay, so we could keep counting up and drawing pictures and doing all of that. Or we could see if there's a relationship going on here. So when there was 1 triangle, 3 segments, 2, 5, 3, 7. Do we notice a number increase or some sort of pattern here?
Up by 2.
Up by 2 for every how many triangles we add? 1. So if we add a 4th triangle, we would have how many? We're thinking we would have 9 segments. So they are asking us if there are 5 triangles. I am okay with a little bit of shorthand. We can use a triangle picture to represent that word. If there are 5 triangles, there would be how many segments? 11 segments. Numbers such as 3, 11, 15, and 29 are odd numbers. Hopefully that's not news to anyone. Make and test a conjecture about the product of any 2 odd numbers. Okay, now we're talking about any 2 odd numbers. So that means we don't have to use the numbers that they gave us. We can use any odd numbers. We are going to make a conjecture, and we are asked to test it. But if you want to come up with some examples first or some test cases first to see a pattern, that's not a bad idea. Okay? I will tell you that your conjecture will start off with the product of any 2 odd numbers. And then we'll fill in the blank with what we observe. So for now, I'll put a ... To be continued. So when we're talking about product, what operation are we talking about? Multiplication. If they ask you to test or give examples, I want at least 3. So I'm going to put mine up at the top. 1, 2, 3. You should have space below your conjecture to put your examples. So we're talking about multiplying 2 odd numbers. Give me 2 numbers to multiply. Kara?
3 and 7.
3 and 7, sure. Those are both odd numbers. 3 times 7 is 21. Okay, 2 more odd numbers. Kobe? 5 and 5, sure, we could use the same one twice. 5 times 5 is 25. We need a third one. 9 times what? 7, sure. 9 times 7 is 63. What do we notice about all of these products? They're all odd. So the product of any two odd numbers is odd. That's our conjecture. Okay, and we went ahead and gave examples ahead of time. We could test it further, but anytime you pick two odd numbers and multiply them together, you will get an odd number. A counterexample is a specific case for which the conjecture is false. I ran myself out of room. Counterexample. It is one word, a compound word. Specific case for which the conjecture is false. So these ones, for whatever reason, sometimes students don't like them, especially once math gets involved. One example would be something like, if today begins with the letter T, then yesterday had to be Wednesday. Can anyone think of a situation where that's not the case? Tuesday, because yesterday would have been Monday. That's a really simple example of a counterexample. Okay, you come up with a situation, even just one situation, where whatever statement you're given isn't true. Okay, so you're saying, no, you're wrong because, and give your counterexample. So, on number 5, find a counterexample to disprove the conjecture. Supplementary angles are always adjacent. Now, it might help that geometry type counterexamples can be shown in pictures. So can anyone think of a picture that we could draw that would prove this to be wrong? Atea? I think you might prove them right. So we could prove them right by giving a linear pair, right? These are supplementary and adjacent. But this proves them right, so that's not what we want. We want to prove them wrong. Deidreana? Do a what? A line with two intersections. Can you sketch on your paper what you mean so I can see? You're getting closer, however, those wouldn't just be supplementary, because for supplementary, how many angles do we want to be talking about? 2. Okay, so that idea was to split it up more, but then we're dealing with 3 angles, and for supplementary, we just want 2. So the word that's tripping us up here is the word adjacent. The opposite of adjacent would be what? Nope. You're making it too hard. Non-adjacent. So if they're saying they have to be adjacent, we want to say no, they can be non-adjacent. So can we draw a picture where we have supplementary angles that are non-adjacent? There's one situation in which that could be true, but that's getting pretty specific. These are adjacent. They share a vertex and a side. So how many angles do we want to draw? 2 of them. Do we want them to touch each other at all? No. And we want to make sure that their measures do what? Equal 180. So there are an infinite, really, amount of possibilities here. We just need 2 angles. How much do you want this one to measure? Okay, 130. This looks like an obtuse angle, so it's reasonable to say it would be bigger than 90. And that means the other angle I draw better be how much? 50. About 50. Okay, now again, you don't have to be an artist. It should look reasonable. But here we have supplementary angles that are not adjacent. They are next to each other, but geometrically adjacent means that they have to share a vertex and a side, and these do not. Now, when people were asking about vertical angles, and I said there's just one very specific situation where that would be the case, is if they are perpendicular and you're talking about those two angles. Yes, technically that would work. They're both 90, they add up to 180. Okay, but other than that, then you'd be talking about linear pairs again if you're talking about ones right next to each other.